Hello everyone, welcome to our DDLC seminar. This week we have the invited speaker, Dr. Yue. And Dr. Yue is a professor of computing and mathematical sciences at Caltech. He was previously a research scientist at Disney Research. Before that, he was a postdoc research in machine learning department at iLab in CMU. He received a PhD from Cornell and a bachelor from UIUC. Professor Yue previously served as Senior Program Chair of iClear 2024 and is this year's General Chair, and currently he serves on the iClear board. Professor Yue's research interests are centered around machine learning and artificial intelligence, particularly in getting AI to work in high stakes and high expertise domains. His work has been recognized with multiple paper awards and nominations, including in robotics, computer vision, sports analytics, machine learning for health, and information retrieval. Professor Yue also worked on machine learning approaches to behavior modeling and motion planning for autonomous driving. And thank you, Professor Yue. You can start with, your presentation.
Great. Can you hear me? You can hear me?
Yes.
Great. Well, thank you very much for the invitation. Today, I'd like to talk to you about some of the work I've been doing with my collaborators the past 4 or 5 years on neurosymbolic AI for safety critical agile control. So first, I'd like to review some of the different paradigms that have become popular over the last decade or so. First, we have supervised learning. And what supervised learning is you have a lot of labeled data. In this case, it's labeled scenes for autonomous driving, where every pixel is labeled with pedestrian, car, road, train, etc. And you collect a lot of these data points, perhaps hundreds of thousands, perhaps millions, perhaps tens of millions, and you feed it into an AI model. And the AI model learns to decode predictions in the exact same semantic space that the labels are in. And this was very successful. And in fact, this is how we trained all the self-driving systems that are now deployed in millions of self-driving cars today. Now, of course, collecting these labels are very, very expensive since they require, in this case, careful human annotation for every pixel. And so what happened is we quickly reached a bottleneck where the lack of supervised labels was what was blocking further progress in machine learning and AI. And so with that came all these ideas in pre-training or self-supervised learning, where you have a large background data set, in this case of images, there's no labels. And then you do what's called self-supervised learning to learn an embedding, which is a piece of an AI model. And this embedding learns to decode features or motifs of the background data set, like shapes or colors or image patches. And then you can use this embedding as a feature representation and fine-tune a small model using a small amount of supervised data. And it turns out that this works really well. And you can sometimes reduce the amount of supervised labels required to train an accurate model by a factor of 100 or a factor of 1,000. So this is very promising. And what we know of as foundation models today, like GPT and Claude and Gemini, are basically these same ideas scaled to internet scale. So you take an internet scale data set, you do the same types of pre-training algorithms, maybe you add some other alignment algorithms like RLHF, and you get what's called a foundation model. And what's interesting about foundation models is that if it's a foundation model trained on text, like a large language model, you can actually just give it text instructions in a prompt. And now you get predictions or decoders. And so what you see here over the last 15 years is orders upon orders of magnitude more cost efficient and time efficient task specific decoding using these large base models as sort of the foundation. And so now we can build AI models for many, many tasks, including in autonomy, including in knowledge work, and including in many areas of science. But as we look to deploy these AI methods into a wide range of real-world problems and real-world systems, we're quickly confronted by the fact that our real-world systems have very complex requirements. So for example, this is a quote from an aerospace director while he visited Caltech. He said, "Yisong, I want to use deep learning to optimize the design, manufacture, and operations of our aircrafts. But I need some guarantees, such as safety and stability and robustness to perturbations. This is also something that is required for things like robotic surgery, where you need extremely precise control. I do a lot of work with NASA and JPL. They want to build robots that explores the outer reaches of the solar system, look for signs of life. The AI on these systems need to be both able to reason about what is interesting science and also keep the robot safe. We know that a lot of the algorithms that drive our social and social media can have propagating impacts on our social and behavioral dynamics. Maybe we want to be able to reason about those dynamics and actually build in guardrails into our social media platforms. In science, scientists are increasingly using AI, and they of course use AI and other tools to make inferences. That's what science is all about, making scientific inferences from experiments and observations. But as we know, AI hallucinates. And so, how do we know that the inference generated by the AI is a good one? After all, you don't want to, retract a Nature paper after you realize that the AI hallucinated a result. And so these are all just examples of extremely complex requirements that an AI needs to be able to at least tell you whether it's violating or not in order for these AI models to be reliably deployed into these types of applications. And to just give you one example that I spent a long time working on, it's in autonomous driving. So, as of 2022, so this estimate is a little bit out of date, there's been $160 billion invested in autonomous driving. And we've made a lot of progress. The progress over the last few years have been incredibly exciting. But at the same time, this dollar amount is huge. It's massive. And what happens, in my opinion, is that you have leaky abstractions, right? These complicated systems are multi-layered hierarchies, multi-layered hierarchies in terms of their software stack and hardware stack. And as you know, you need tight abstractions in order for these autonomy stacks in any software stack to work well. If you have leaky abstractions, then the engineers need to basically deal with many corner cases on an ad hoc one-off basis. And that leads to heavily engineered systems that are difficult to maintain, difficult to debug, difficult to extend. And this, in my opinion, is the core cause of why it costs so much money to build to have developed and researched an autonomous driving system. For example, if you write in Python code and you use the sort function, you don't want the sort function to sometimes not work. You could never use the sort function, or at least if you did, you have to have a bunch of corner cases to check it in case the sort function doesn't work in a few corner cases. And so my thesis is that strong abstractions enable building complex systems. They are interfaces between components. They are contracts that should be satisfied. A sort function says, I will sort any list. You believe that it will sort any list. That is actually a contract. And it thus empowers cost-effective debugging and verification at scale. And so for the rest of this talk, I will be giving you a case study in thinking about this idea of contracts and AI in the context of agile robotic control. So for example, how do we build AI systems that can intelligently deal with boundary conditions, dynamic environments, while ensuring safety, sharp disturbances, human-robot interactions, and multi-agent interactions. So these are all projects that I've been involved in over the last few years here at Caltech. Okay, so first, just to put everyone on the same page, we're going to go through a super simplified description of a standard autonomy stack. So here is a scene at Caltech. You have a drone. First, the drone does some perception and sensing. Then it does some high-level planning. And then it actually executes a sequence of control actions to realize the plan. And in a real world, you got to deal with other agents. You have to deal with wind and other disturbances. You have to do precise control around barriers and other boundary conditions. You may be carrying a payload which perturbs the dynamics of the system that you need to adapt to. So these are all requirements. And of course, we want to solve these things using AI. And so what you have to a first order approximation is you break down the autonomous system into perception and decision making. So, and in reality, of course, it's not just a layer of decision making or perception, it's multiple layers of decision making and perception. And what I'm basically advocating for is that as you put AI methods and machine learning methods into these different layers, you want those AI systems to yield or satisfy desired certificates between the layers. And so the focus of this talk is to think through just a small piece of the stack, which is the interfaces between low-level decision-making, high-level, and medium-level decision-making. And I believe that you can actually use AI to help optimize any aspect of this. So you could do system-level design. You know, how do I design this whole stack? You could design the individual abstractions and certificates. And of course, you can design individual components that are designed to satisfy certain certificates. In the bottom side, the abstractions and certificates basically can be compiled into a learning signal or a reward function. And then you could optimize the components to satisfy those certificates. Conversely, if you have a component that's a little bit black box, you can actually do various statistical tests to deduce what can be certified. On the right side, we have essentially programming, right? You can, we use foundation models for programming all the time. You can actually do system level programming and library design, designing a library of certificates. And on the left-hand side, of course, is end-to-end learning, right? If your system is designed in a way that is end-to-end optimizable using reinforcement learning or end-to-end differentiable, you can do end-to-end learning. So I believe you can use AI to optimize any aspect of this design. So the research questions I studied while doing this case study are things like, how do I define abstractions to capture system level requirements? How do I use those abstractions to constrain learning to satisfy those requirements, and sometimes provably, in which case we have a certificate? How do we exploit the structure arising from these abstractions and constraints for faster learning, both computationally and statistically? And then how do we interpret this whole thing that we're building as a unified neurosymbolic AI system with both neural components and AI and symbolic components? And so the rest of this talk, I'm going to talk about two projects. First in residual model learning, and then in policy optimization for underactuated controllers. Let's start with the first one. So this is the work of the neural control family, which was Guanya Shi's PhD thesis work. Guanya has since graduated, and he is now an assistant professor in the Robotics Institute at Carnegie Mellon. And so the basic idea is that you want to build a model of dynamics that complements the symbolic model dynamical system model that we use typically for drone flight. And we do it in a way that satisfies certificate requirements and is useful for reliable downstream controller design and trajectory planning. And so where did the challenges come from when we actually want to fly drones in various kinds of adverse conditions? They come from uncertainty, such as wind, which is often highly nonlinear, non-stationary. Computational data efficiency. We want things to run on board on commercial drones. And of course, we want these certificates. This is sort of the main point of this talk. Neural networks are notoriously hard to analyze. They have, they're not smooth. They have tricky function landscapes. And so how do we actually combine that with the kind of certificates people care about in control? So one example that we looked at for about a year or two is boundary interactions. So if a drone was to interact with a boundary condition, in this case, it could either be another drone or it could be the ground. That perturbs the nominal aerodynamics that people use to model drone flight, and that can cause the drone to destabilize or to behave poorly. And so we're going to take a model-based control approach, which is the standard approach in most drone controllers. You have your normal dynamics model. It's like a 12 degree of freedom or 16, 18 degree of freedom ODE model of a drone. Pretty simple, pretty basic, pretty straightforward, very standard for decades. What we're going to do is we're going to augment it with a learned model that can capture things that are very difficult to model using your symbolic model, such as in this case, the downwash or ground effect. We're going to do this in a way that yields certificates on things like stability. And these certificates can then be used or consumed by a controller to build a stable and robust controller that you can use for trajectory planning. So that's the idea. And so this is probably a review for everyone in this audience. I give this talk to a wide range of audiences, including those who work purely in AI. The standard model-based control idea is just a dynamical system, right? You have a change in state that depends on the current state and the current action plus whatever you're not modeling. And most methods in robust and optimal control, I would interpret as fancy versions of contraction mappings, where you want to make sure that you're always contracting towards the desired state, even in the presence of disturbances. And then you do various types of analysis based off contracting potential functions like Lyapunov functions in order to prove these guarantees. And the precision of the contraction depends on the size of this error epsilon. And as a side note, for those of you who study reinforcement learning, there are many methods in reinforcement learning that are also contraction mappings like value iteration. So the basic idea, the game that you play, is you want this unmodeled error epsilon to be as small as possible. And so you add this extra model, this learned dynamical model, which is typically a neural network, G. And the idea is that I want the exact same structure of my model. I want all the certificates from contraction mappings to be preserved, but I want the precision to be much, much tighter because epsilon is much, much smaller. In other words, I want to preserve stability of my dynamical system, even using deep learning, provably, while epsilon, the error, is much, much tighter. And so, mathematically, what this looks like, if you were to actually write out the full math, it would look like this, right? So we don't care about the blue part. We just use off-the-shelf stuff. It's the red part that we're going to add to it in a very, very specific way. And so the controller that you would use, you can use any controller. You can use, simple nonlinear tracking controllers where, in this case, if we're doing landing, so there's an unknown ground effect. And this is the error because we're not landing as accurately as we would like to because of the ground effect. And basically, all we're saying here, this is a very standard controller design, is we just literally just add our learned model into the input of the controller and we're done. So we don't want to mess with the stack. We don't want to make things super complicated. We just want to actually make the system much more accurate. So you could use very, very simple controller design. That's the goal. Okay, turns out simple integration doesn't work. We tried this for a while. Guanya tried this for a while when he was a PhD student at Caltech. You learn a neural network of these residual dynamics, you plug it into the controller, you run the controller crashed. The drone crashed multiple times. And there are a few reasons why. The first reason is that the neural network had a hard time generalizing outside of its training data. So once it leaves its training domain, which happens rather quickly, it starts making bad predictions. And then the error actually goes up, not down. Secondly, because it's a neural net, the its input-output behavior is not smooth. It can be very steep. In other words, G has a bad Lipschitz constant. And so this is actually the thing that causes both of these things in combination, but especially the second one, is what causes the certificates to be satisfied. Because in order to prove a Lyapunov analysis, you often need things like, the dynamical system is Lipschitz smooth or something like that. And if you don't have that, your Lyapunov or contraction mapping actually the proof breaks, the certificate breaks. And so, in other words, these properties of this neural network violate stability and accuracy certificates. Okay, so then how do we build a neural network that can satisfy these certificates? So, so in order to sort of make progress on this, you sort of take one of the existing ways of analyzing stability, and you kind of really break it into pieces and then redo it, in order to expose the actual requirements on the neural network. And so here's a theorem that we proved. The theorem itself is, nothing too crazy. It basically says that if our neural network model of the dynamics is L Lipschitz, for L less than some system parameter gamma, then the downstream controller will actually converge exponentially fast to the desired trajectory to a radius of that depends on this approximation error. Now, this theorem is like many other theorems you see if you take control theory 101, right? And gamma is a system-dependent threshold. And you use the same proof techniques, which is to show that the downstream controller is a contraction mapping. So nothing here is that different. The novelty is to surgically dissect and rebuild this type of theory in order to cleanly expose the requirements on the neural network. What do we require the neural network to satisfy in order to prove this theorem? And then for a controller to use this theorem, to have a provably robust and stable controller, then for a trajectory planner to use that. And interestingly, this gamma parameter is actually necessary. Different drones have different gammas because they have different sizes, different mass, etc. So, okay, we've determined that we need to constrain the Lipschitz constant on neural networks in order to use these types of certificates. So we use the method called spectral normalization. I'm not going to talk about it in detail, but it's a standard method to constrain the Lipschitz constant of the neural networks. And so here you can see an actual experimental result where we collected real-world data, and the green points. So the x-axis is height, the y-axis is the ground effect. The green points are the actual experimental measurements. The blue line is our neural network's predictions. And the red lines are various, physics-based approximations, symbolic approximations. And you can see that our method is extremely accurate here. The error is very low. And moreover, because we're doing this Lipschitz constraint, the model's behavior is actually very smooth. So on the right-hand side, what I'm showing you is the x-axis is landing velocity. So -2, -1 here means we're landing at 1 meters per second. And the y-axis is height. And we only collected data over here on the right-hand side of both of these plots. And so you ask the question, okay, suppose I train this model on flying, relatively slowly close to the ground. What if I wanted to land much, much more aggressively? And you see that the neural network that doesn't have this kind of Lipschitz constraint generalizes extremely badly. Its prediction behavior destabilizes. And this is what causes the drone to crash, what you see on the right-hand side here. This is literally what causes the certificate to be violated, what causes the whole stack to crash, because this assumption was violated, the certificate was violated, the whole system crashed. And this is what I call a leaky abstraction. So here's a demo. So you see this drone. It is flying extremely close to the ground. This is a commercial drone, by the way. It's a drone you could buy off the shelf. The only thing we added with this was this neural net. It is flying extremely close to the ground, not touching the ground. And we can, in fact, prove via our certificates that it will not touch the ground. You could do the same thing, just fancier, scaled up to things like swarms. So this is the Neural Swarm project. Normally, when you buy these commercial drones, there's a warning label that says, do not fly it within 3 meters or something from anyone, from any other drones, from any boundaries, from any humans. And that's because, the controller is not accurate, and, the dynamics model gets perturbed, and, things like that. So you can take commercial off-the-shelf drones, add a neural net that understands how to model drone-drone interactions in a way that's accurate and stable, and then you can achieve extremely tight formations like this one. Again, using commercial drones, off-the-shelf controllers, everything's very basic. You just added this neural network that understands what's going on when you fly close to another drone. So these drones are completely mechanically capable of doing stuff like this. Just before this type of work, they weren't intelligent enough. And they didn't have the intelligence in a way that is sort of certifiable, so you can build an entire autonomy stack on them that has safety and stability guarantees. So the story so far is, we have this stack where we build this model of these complex dynamics, and we, have all these certificates that get propagated up the stack. So we tackle challenges like uncertainty, efficiency. So I should mention these neural nets are really tiny, and these certificates. You do this in a way that has these certificates that propagate all the way up the stack. And, I mentioned before that this gamma, the Lipschitz constant needs to be smaller than some platform dependent parameter gamma. So for the drones, the big drone that you saw, gamma was 16. And so you have to constrain the neural network to have Lipschitz constant of less than 16. If you don't use this constraint, you just train a neural network naively, the Lipschitz constant was actually about 8,000. And this is literally why the drone crashed. It destabilized the entire software stack, control stack. Okay, so I'm going to briefly talk about NeuroFly, then I'll move on to the second part of the talk. So in NeuroFly, the disturbances that the drone is being subject to are time varying. So, for example, this is a wind array. This is the Caltech wind array, fan array, and the drone is trying to regulate towards this block, but it's unable to because of the wind. And the wind is very complicated. It creates a nonlinear effect on the drone, as you can see when we added the fog, the smoke. Okay, so the key idea is that we want to adapt the controller to the environment. And so we developed a method called meta-adaptive control. So phi is a shared representation that does not depend on the environment. So it's domain invariant. And then we have an adaptation coefficient A or alpha that will adapt online to the environment. So this is linear adaptation using a learned representation. And so, I'm not going to go into too much detail here, but the basic idea is, you learn this residual model G in a way that you have this shared representation phi that then you could do linear adaptation on. The reason why we do linear adaptation is because linear adaptive control is something that's been studied for about 50 years. And it's very well understood. What's not well understood is what representation you should be doing adaptive controlling, because linear is in many ways very limiting. So all we decided to do was to learn a good representation so that you could do a linear adaptive control. And again, once you do that, you can prove the same types of results. In this case, we're just adding the theory of linear adaptation onto the results. So, that's at a high level what we're doing. And then you get, and of course, learning is imperfect. And then you get a result like NeuroFly, which was published in Science Robotics. So here you see this drone flying through this obstacle ring with varying wind conditions. So the wind varies between 3 meters or 1 meter per second, and I believe 5 meters per second. And I just want to emphasize that this obstacle ring is very small relative to the drone. The drone has very, very little clearance, and it's doing extremely precise trajectory flight control through this dynamic wind condition, through these obstacle rings. And I just want to emphasize again, this is a commercial drone you can buy. They're all mechanically capable of doing this. The only reason they weren't able to before was because they weren't smart enough. And you could not build a reliable control stack for this. Okay, so just to conclude this first part, this very last bit we did to quantify uncertainty, we did a meta learning approach to learn a general representation. This allows us to do adaptive control for varying environments using linear adaptive control theory, and you get the same certificates. Okay, as an aside, what I showed you thus far is residual model learning, where you learn this model to complement a symbolic model. You could do the same thing at the policy level, right? You could have a symbolic policy like PID control, right? You could have a symbolic policy, and then you could actually learn a policy at this layer to complement the outputs of a symbolic policy. And so you could do this. You could do this as well, and also get various types of guarantees. But I'm not going to talk about it here. Just to mention that this is an alternative approach that you can take as well. And I'm happy to share the slides with the audience, with the organizers after this talk, so you can check out the references if you're interested. So the second part of this talk is on policy optimization for underactuated controllers, which I think is pretty interesting. So the motivation, as I alluded to many times, is underactuated agility. So a system is underactuated if the degrees of freedom of its controller is lower than the degrees of freedoms of the system, and it's often severely lower, much lower than the degrees of freedom of the system. And so just to use a simple biped just as an example, here, this biped has 4 joints in red. That's what you can actuate. But what we really care about is the angle. Well, one of the things we really care about in this example is the angle that the foot hits the ground, because that determines whether the robot falls over or not. But you don't actually control this, right? You control this indirectly through these 4 joints. And so mathematically, there's a control matrix, and this point is in the null space of the control matrix. That's what's happening here. There's other things going on, like discrete dynamics, because there's collision and contact, but I'm not going to emphasize that in this talk. So here's the key idea. If you want to build a software stack, a control stack, with certificates that propagate up and down the stack. If you're always on the controllable manifold, you could use any policy optimization approach you want, because you could just inherit any of the other guarantees that you want. In other words, if we ignore the uncontrollable parts, the null space of the controllable manifold, then we can do whatever we want. So the key idea in building a controller is to cancel out the effect of the null space of the controllable manifold. That's the high level idea. There's a lot of math here that I'm brushing under the rug, obviously, but this is the high level idea. So, for example, I know that if the swing foot of this robot, just in the simple example, the swing foot never it touches the ground at a certain angle, within this green region, I know that I'm approximately on the controllable manifold. Or if the torsal angle is always in this region, I know that I'll always approximately stay on the controllable manifold. These are constraints given to us by a robotics engineer who's an expert, a domain expert. And you can think of these as sufficient conditions to stay on the controllable manifold. So in other words, they're conservative. But let's say we have them. Then we can treat the policy as continuous time map. So we assume that the dynamics model is known in this example. We just want to learn a policy that satisfies these specifications, such as on the torsal angle and swing foot. And so we're going to parameterize the policy as a neuro ODE. And so what happens is you have a reduction step that reduces the full control problem into two problems, which is satisfying the constraints to stay on the controllable manifold, and then optimizing, your desired learning reward function or cost function. And you want to do this in a way such that once you satisfy these requirements in the reduction, you inherit various types of stability and robustness guarantees. So we're going to do this in a way that's probably not too surprising. We're going to capture these requirements as a potential function. And the potential function is large if this requirement is being violated or close to being violated. For example, if the torsal angle is leaving this region, this potential function or cost function becomes very large. And so we're going to, analyze stability via contraction. So this is probably not too surprising for many people in the audience. A potential function v that we want to be small is considered contracting over time if its time derivative is a function of itself, right? That's what this means. That means it's contracting exponentially fast. So an exponential function is the only function class where the derivative of the function is, or the slope of the function is proportional or equal to its current value. That's a special property of exponentials, and that's how you get to this invariant. So this shouldn't be too surprising, but once you can prove this kind of property, you get a range of certificates. And so we certify our Neuro ODE by having it as part of its learning process, learn to satisfy this contraction certificate. So here is just a 2D Neuro ODE, and the green parts are where the blue parts, excuse me, are where this contraction condition is satisfied, and the red parts of this Neuro ODE are where the contraction condition is not satisfied. And what we want is to learn in Neuro ODE, which is our policy, where the entire state space is blue. Then we can show that the Neuro ODE is contracting so that it never violates these kind of constraints that the robotics engineer puts in, like, don't have the torso be too out of stability region. So in other words, if we can satisfy this contraction condition everywhere, if this entire region was blue, then we can prove stability guarantees that we can propagate up the software stack. And of course, there are many types of contractions. There's stability towards a set. There's forward invariance or barrier functions, never leave a set. And we're going to use, of course, barriers for this example, but this is just an implementation detail. So what we did to be able to develop a machine learning approach to be compatible with this type of control theory is to develop what's called the Lyapunov loss. So first I'm going to show you the pointwise Lyapunov loss, which basically is like a hinge loss, if you're familiar with support vector machines. It basically says, if H is a point in my state space, if my dynamical system, my Neuro ODE, does not satisfy the contraction condition at this point in the state space, then I pay a loss that is equal to the amount of contraction condition violation. Or if I am satisfying the contraction condition, then I'm paying zero loss. Okay, so that's the entire loss function. And then the entire Lyapunov loss is just the integral of this loss function, over the whole behavior of my Neuro ODE. So achieving zero Lyapunov loss almost everywhere implies exponential stability, essentially by construction, just by the definition of Lyapunov loss. So that leads us to the LyaNet framework for training Neuro ODEs. This is work led by my student, Ivan Jimenez Rodriguez. So you interpret any requirements from a robotics expert as a potential function. You instantiate the pointwise Lyapunov loss in the following way, and then you optimize Lyapunov loss everywhere. Now, there's a few optimization considerations. So evaluating the integral inside of this expectation is actually very hard, often intractable. So we approximate it by sampling. So you sample a bunch of points at uniform, and then you just sample points, and then you see if the Lyapunov loss is violated. If it is, you induce a gradient. If not, you don't. So this is something we've already implemented in PyTorch. All it does is it samples points in a state space, measures the Lyapunov loss, and it induces a gradient that backprops onto the neural network if it's violated. So that you can try it out yourself. The benefits of sampling: you avoid an expensive ODE solve. And so you're essentially trying to minimize, if you just do uniform sampling, you're essentially trying to minimize this Lyapunov loss under a uniform measure rather than the measure induced by your neuro ODE. But the goal is to get to zero loss, so you could use any measure you want, really. And similar ideas are used in diffusion models when they do sampling to optimize the score function. The main difference between this approach and diffusion models is that in diffusion models, you try to satisfy an equality constraint, which is score matching. Whereas here, we're trying to satisfy inequality constraint. That's the main difference. Okay, so back to the application. So we have these constraints that are supplied to us by a robotics engineer. We're going to compile them into a potential function, compile that potential function into this Lyapunov loss, and then optimize it in PyTorch. We deploy the controller, and then we try it again, and we repeat. And so that leads us to neural gates. Again, this is a relatively simple biped, but I think what's interesting about this result is that we can prove forward invariance. We can prove that this robot, under these conditions, will never fall over and walk forward indefinitely into the future. So I think that's an interesting result. And you might be asking at this point, okay, your proof actually you don't have a proof maybe because you're sampling. You're just sampling points, so you only show that in expectation over the points that you sampled, you achieved no violation of the certificate. Turns out that you can do a bunch of tricks leveraging active sampling or adaptive sampling and some formal verification to actually certify even with sampling. And this is, to my knowledge, the first robust forward invariance certification result on these higher dimensional systems with neural networks that have been produced. I'm not going to go into details because it's a bit technical. The key ideas is, sampling and some extrapolation using the Lipschitz constants of the neural network. But let's come back to this original motivation for the second part of the talk. The goal was to cancel out any effect that would cause us to leave the controllable manifold. And we asked the robotics engineer to supply sufficient conditions, which are these two examples you see on the right. But these are sufficient conditions. That means they're conservative. And because they're conservative, they're not optimal. So this is maybe less of an issue for this application for walking. It becomes a huge issue for something like a one-legged hopper, because actually we don't know how to specify sufficient conditions for this that are not overly conservative, so conservative that the system doesn't even run. So here you see that we're pushing the hopper, kicking it, it doesn't fall over, and in fact we can prove that it doesn't fall over. I'll show you how we do that in a second. It can walk upstairs, and this is actually quite complicated. Again, it is a one-legged hopper. They can easily fall over, but it doesn't. It can go up the stairs. You can walk a plank. Again, if you don't have stability certificates, it can easily do something stupid like fall off the plank. And then, you can deal with all sorts of weird obstacles. And this is a simple system, but it's interesting because despite being a simple system, it's actually really hard to write down certificates that keeps the robot on the controllable manifold without having those certificates be so conservative that the robot just doesn't even function. All it does is hop in place. So the basic idea is you realize that you can actually generalize these ideas to something where all you need is two things. One, you want to stay on the controllable manifold. And two, once you're on the controllable manifold, you do policy optimization to minimize cost, right? To have an optimal controller. And once you write it like this, express it like this, you can actually just express this as a loss function directly and then optimize it using the similar techniques that I showed before. You don't need to have an intermediate step where a human interprets what it means to stay on the manifold. and then writes down these rules that are conservative. You can actually just directly write down your system and express this as an objective, and then everything actually auto compiles. So that's how we solve this problem. Okay, so many specifications are combinations of stability, invariance, optimality, and robustness. You just write them down as requirements in the most abstract way possible. And then you can then just compile them using a series of reductions into something that we can directly optimize in PyTorch. And then once the controller is optimized, you get a policy back that satisfies many of these specifications. And then you could use it for various other applications like trajectory planning, et cetera. In other words, we learn through a series of reductions and compilations, we can learn to directly satisfy these properties, which produce certificates that then you can inherit for up the control stack. Okay, so moving forward, obviously, what I showed you was just a small piece of this whole autonomous system stack. Right? Obviously, one thing that I'm really interested in now these days is system programming using things like foundation models and LLMs. Why we can actually imagine how we can redesign the entire stack, just program it, and then specify the certificates, and then use these methods I described in this talk as tools or subroutines to then optimize the whole stack. I think that's really exciting. Obviously, on the right-hand side, you also want to do perception with certificates, which is actually quite challenging because perception deals with pixels. Pixels are extremely high dimensional. As an aside, you can do these things with other types of control, like music control. So one of my projects that I worked on, this received an oral presentation ICML last year, is to do rule-guided control of music to satisfy constraints specified by a musician. So basically, in these examples, an expert musician, a professional musician, specified musical rules, like different progressions, and then you generate music that's consistent with those rules. And here he is playing with the music. Okay, and then I want to end with just some thoughts about perception. So I'm actually really interested in perception as well. I decided to study it in the context of scientific imaging with my colleague, Katie Bauman. Katie, for those of you who don't know, she led the team that imaged the black hole about 5 years ago. And so she's an expert in computational imaging. And the basic idea here is that you take measurements from, let's say, a telescope, and the telescope measurements are extremely sparse, and you have an algorithm that tries to reconstruct the phenomenon. And the imaging algorithm that tries to reconstruct the phenomenon is actually a neurosymbolic algorithm. And the requirements here are a little bit different than in autonomy, but what a scientist requires is whatever you reconstruct should be consistent with known physics, and whatever uncertainty you have, this is extremely important. If you have uncertainty about what you're reconstructing, they need to be calibrated. They need to be able to give you p-values, because otherwise you can't do scientific inference properly or rigorously. So these are the types of requirements that are needed to build a neurosymbolic system for scientific imaging. And so, here's just one result that appeared at NeurIPS last year, where we're able to blend physics and learning methods to yield, in this case, we've got black hole imaging techniques that are both extremely accurate and have proper posterior sampling in the sense that the uncertainties are calibrated. So you can think of this as a neurosymbolic AI system with certificates on uncertainty quantification and consistency with physics. So, all the materials that I talked about today are published or on archive. So here are some references. Again, I'm happy to share the slides with the organizers after this talk. And thank you for your attention. I'm happy to take some questions.
Thank you, Professor. Let's wait for the audience to type the questions. Let me ask first, maybe. So I have one question. For the first part of your work, you learned the residue model. So I was wondering, like, this residue model should be like task specific, or is can be like generalized for different like tasks. For example, you show the drones they're gonna be fly on like near close to the ground. This can also like it is gonna be like specific for this task, or this residue model you learned can be handle also other scenarios.
Um, so, so I think it ultimately depends a bit. So there's two ways to answer this question. There's the research way, and then there's the sort of applications way. On the application side, I think the roboticists will say, well, it's just whatever works better. So for example, this model actually the model for this in these drones, they can handle many kinds of effects. Any effect that that puts a boundary on its aerodynamics, whether it's other drones, whether it's people, whether it's the ground, whether it's anything, this can model. So this can model any boundary condition that perturbs its aerodynamics. So normally, the symbolic model of a drone dynamic is free form. So the drone is in air. There's nothing that's constricting the airflow around the drone. So it just pushes air down and it flies. The moment anything else enters its airspace, it puts a boundary condition on its aerodynamics because there's something that's blocking the airflow. And so this neural network, the single neural network can model actually all of it. Now you can say that's one category of perturbations, right? It's a category of perturbations that we can just model for all possible sources. In here, we had NeuroFly, which actually did meta learning. And so what this means is this neural network is learning to be useful for any kind of wind condition. It could be slow, fast, it could be spiraling, it can go in different directions. It can actually, and the diversity of wind conditions is actually quite diverse. But again, it's a category. But so I guess from a robotics point of view, from an applications point of view, you may want to split it up into different categories and then learn a single model for each of those categories. But ultimately, I don't see why you can't learn a single model for everything. But that's more of a research question.
Thank you, Professor. One audience asked, could you elaborate a bit on how you learned the linear adaptation for adaptive control you mentioned?
Sure. So I don't have actually, let me see if I have a slide on this in the extra slides. Give me one second. If I don't have an extra slide, I'll just go back to that slide. Okay, let's see. Is this the right slide? So how this works, is you collect data from multiple wind environments. So K here indexes the different environments. And then you put in this learning objective where you learn a single phi across all wind environments. And then for each individual environment, you learn a specific linear coefficient. And this coefficient is meant to track the disturbance, which is why, sorry, the notation, I pulled it straight from the paper, so the notation is not consistent. I apologize. So Y here is the disturbance from the wind, and phi is the representation I learned across all environments, and then A sub K is the linear coefficient. So this is just linear. This is a linear composite adaptive control. It's something from Slotein's textbook on adaptive control.
Thank you, Professor. Another audience asked, could you please explain the details for the underactuated control part?
Let's see. Do I have details? Oops, sorry. Sorry about that. Let me go back. Sorry. So basically, in underactuated control, in normal control, you assume that you can sort of in normal control, you assume that your control gain matrix is like full rank. If you if you look at like a standard, like if you look at the standard theory for like LQR, linear quadratic regulation, you assume that the gain matrix is full rank. If the gain matrix is not full rank, actually it doesn't work. There are certain parts there are certain things you can do that you do there, like the Riccati equation, like it can't like it just doesn't work if it's not full rank. So basically, because the gain matrix is not full rank, you can't do everything you want. And in particular, in this particular example, if this foot, if the torso, this is more intuitive. If the torso is too leaned over, you are going to fall over. You're going to fall over, and there's nothing you can do because you don't actually, because once you've tipped over, your foot's no longer even touching the ground properly. So nothing you control from these fork joints can stop you from falling. And so like your gain matrix at that point is like almost all zero. It's almost all zero at that point. So that is under actuation. For those of you who've studied sort of the basics of control. And so you have to do something to deal with that. That's what this is about.
Thank you, Professor. I have one last question about like the at the end, like you mentioning when we have like hierarchies like requirements with reduction, we're gonna kind of even we don't know some specific requirements from expertise, but we can still like kind of reduction the state space, like we not state space like solution space, so we can have the optimal solution. But so this optimal is not like the global optimal, but it's like way more better than the conservative solution.
It actually is, well, okay. Under the definition, under how you define the problem, it is the global optimal.
Okay.
And that's because we're exploiting the power of deep learning. Yeah, I mean, if you could achieve, well, okay, let me back. It can sometimes be the global optimal. It's whatever it depends on how well you learn, right? We reduce it to a problem where you have to run it on PyTorch. Yeah.
Okay. Thank you, Professor. Thank you today for the interesting talk. If you could send me the slides, I can add to the web. Also, other people, if you are interested for the reference, they can have a look.
Thank you.
Okay. Thank you.